So now that we've looked at what it takes to make a really good start to your poster, that is with the aim, hypothesis, and the background information, we're going to start looking now at the methods and the results. That is, what is it we actually did, or what is it you actually did in your IRP, and what were the outcomes? That is, what was the data that you collected and what trends might they be showing? Okay, so if we start with the methods, this is the section, it's kind of like a recipe, okay, if you're thinking about it like that. It's a way of just outlining the procedure that you took in a very detailed manner. Now, I use the word recipe in a sense that a lot of people like to start off by using a list or steps that they took to complete their experiment. Now, this is not a bad starting place, but eventually as you progress throughout your schooling career, you'll want to be moving away from just simply putting down lists and converting it into a full paragraph that flows on with sentences and things like that. But for your post, it was fine just to have steps. Okay, so the idea behind the methods section is if anyone wanted to repeat your experiment, they could do so simply just by looking at your methods. For that reason, it needs to be sufficiently detailed, okay? And we'll go through exactly how we were expecting you to outline that detail. But at the same time, we don't want it too over the top, like too much detail. So we need to find this nice balance where there's just enough information. At the same time, it's not like, wow, this is so much information, I don't know which part's important or whether or not I really need to use that 1 meter ruler compared to a 30 centimeter ruler. So yeah, anyway, we'll go through that in a moment and just confirm we all understand what it takes to make a good methods section. Now for your poster, we broke the sections down for you so you can understand the different aspects of what makes a good methods paper. And these 4 sections were the variables, your equipment, the steps or the procedure that you took, as I was mentioning before, as well as we wanted you to include some safety analysis or a risk of any sort of danger that might be involved in undertaking this experiment. Now these are all aspects of what it would take to make a good methods. So you need to understand what are your variables, like your dependent, independent variables, you know, so we can understand exactly what you're testing, as well as all the necessary equipment, just so if someone across in Germany, for example, or anywhere else in the world, wanted to make sure that they're getting the same results, they wanted to use the exact same equipment potentially. So yeah, we'll just go through each of these in turn, and relate that to the outcomes of your IRP. So I'll start off with explaining what we were looking for, and then I'll give some examples of what a good response would have been. Okay, so let's start with the variables. So in terms of our marking scheme or the marking rubric, to get full marks for this section, that is including your variables, you needed to have all the variables included correctly. Okay, so sometimes people mismatched or they identified a dependent variable as an independent variable or vice versa, or sometimes they had the dependent and the independent listed as the same thing. So that's okay. You're still learning what's the difference between all those different types of variables. Hopefully, I know in my classes I went through quite strenuously about these different types and how to identify them in an experiment, but I'll just quickly go through the different types now. Okay. I should also mention, sorry, before I move on, a lot of so we usually refer to these things controlled variables here. I sometimes, just because of my scientific training, I call these standardized variables. Now, please don't get confused. They're still what we will call at school controlled variables, but I just like to use the word standardized because sometimes if we use the word control variables, sometimes we can get that confused with the control treatment, okay, which is something slightly different, which I'll talk about in a moment. But in any case, if you hear me talking about standardized variables, I'm really just talking about the control variables, okay, the things that we kept standard in our experiment. All right. So let's just use the plant experiment, that is where we kind of changed the environment that these seedlings were growing in to see what environmental factors influence their germination or growth. Now, we probably already don't need to rehash what the hypothesis would have looked like, but In terms of identifying potential independent variables, okay, we would have first said, okay, what is the things that we're changing? These are the independent variables, okay? So what you as the experimenter are interested in finding out, okay? So I have a list of things that you could have done. I'm not saying you had to do all of them. So many of you just would have chosen one of these and investigated this properly, but some of you might have stepped up a level and tried to do two at the same time. Okay, so some of those might have been the amount of water. So how much does the amount of water affect the growth or the germination of seedlings? Secondly, the amount of light. I know a lot of my students, they chose this one because it was easy enough to put some in the cupboards and some out in the light and see what that sort of had an effect. So basically light or dark. Some of us, not a lot of us, chose to change the amount of nutrients or fertilizer in our experiments, and some, not many, chose to change the acidity of the substrate or the soil. Okay, so these are all independent variables or examples of independent variables. Now sometimes if we choose just one of them, the other factors might become what's called standardized variables or control variables, okay? And I'll explain how that happens, but I understand that you might have got confused here and maybe not included them as standardized variables because you thought they must have been independent variables that you just didn't include. But yes, you need to be able to control all the things you're not testing, okay? So the next type of variable is your dependent variable, okay? Now, these, is the way I describe it, are the things that you will be measuring. So seeing what sort of response your treatments, that is your independent variables, what sort of response that has or effect it has on your dependent variables. Now, I noticed a couple of the reports that I was marking, they included some of the standardized or independent variables as dependent variables. I think there might have been some confusion just because they might have been measuring the amount of light, for example, in the dark or in the light, but that doesn't make it a dependent variable. It's still the independent variable. It's just that you're confirming or making sure that your independent variable is changing the environment as you would have expected. Okay, so not everything that we measure in an experiment is a dependent variable, but when we're looking at the response, that is what we're measuring. I hope that makes sense. I hope that's not too confusing. I think I might have even just confused myself. Anyway, let's move on. All right, so some things which you might have considered as dependent variables would have been, this was the most common one, time to germination, represented in the number of days since the experiment started. Growth rate, okay? That is number of centimeters of the plants grew per day. Okay, now growth rate is different to what we might have called as final height. Okay, that is at the end of experiment, how tall were each of your seedlings. And another thing you might have chose to measure was final weight or biomass. Okay, these are all dependent variables that you could have measured if you were using the plan experiment or the plan option. Okay, now they're the two easiest things to start with in terms of listing your variables. The hardest one actually is these standardized variables. You're going to have to think outside the box and kind of think, well, what's all the other possible factors which might be influencing my results? And if you can think of anything, then you have to try and standardize it so you know it's not influencing your dependent variable. Okay, so sticking with the plan experiment, these are some of the things you could have thought of about controlling. So for example, the number of seeds. If you put more seeds into a unit area, then you increase the competition between those seeds and therefore they might not grow as well. Okay, so you might be looking at a confounding effect of competition, not just whatever you've decided to change. Also, you want to keep standardized the amount or type of soil, because if you're using soil, for example, there's nutrients or other things in the soil which might influence the growth of these seeds. So you want to make sure that each of the seeds and each of your treatments have the same amount of access to those nutrients or substrate. Another big one is you want to make sure that between your treatments, the external environmental conditions are relatively the same, or if not exactly the same. So temperature is a big one here. If you're not manipulating temperature, then you want to keep that constant, okay? Because you don't want temperature to affect the growth of the plants. And fourthly, the size of the container might actually have an impact depending on how big your plants grow. If they start getting what's called pot bound, or they start running out of room, that might influence their growth as well. So you can see all these things, and there's probably more. I haven't mentioned more here, but these are just some of the what I call standardized variables. Okay, things you have to keep the same in your experiment to make sure that you're actually seeing a difference because of your independent variable that you've changed. Now, you heard me mention before about a controlled treatment. Now, not every experiment can or should have a controlled treatment, but in some cases, it's actually good to include a controlled treatment. Now, this is just to test to see if anything about you as the experimenter or the way you've designed the experiment is influencing the results. So, for example, if we keep sticking with the plant experiment that some of you did, if we had chosen to use soil, okay, the soil themselves might actually have some dormant seeds that we were unaware of, okay? And unless we use a control treatment where we just have the soil without any seeds that we put in ourselves, we really don't know if the seeds that germinated are the ones that we planted, okay? We assumed that the soil, if we use soil, didn't have any seeds, but we don't know for sure. So that's why we have a control, just to make sure that nothing would have happened if we added no seeds, okay? Likewise, you might think, okay, well, a treatment without water, that's also just to see, you make sure that nothing happens if we don't do anything to it, okay? So this is what I mean by a control treatment as opposed to a standardized or controlled variables, okay? All right, that's just the first section of your methods. I can see some of you are probably thinking, oh my goodness, is this what it takes every time I need to do an experiment? I'm just going in a lot of detail now, so in the future, it won't take as long to think about it. And you can easily just go, yep, they're my different types of variables, list them down there. All right, so equipment. This is pretty self-explanatory, okay? The only thing that we were really kind of looking for to give you full marks was it's not only just list the type of equipment, but we wanted you to kind of, if it was necessary, to have some sort of size, measurement, or detail. So for example, if we consider the physics option where a lot of us got some objects and rolled them down a ramp, it wasn't good enough just to say as one of your equipments, ramp, okay? Well, what sort of ramp? Was it made of Teflon? Was it made of sandpaper? Or was it made of smooth wood, okay? And how long was the ramp, okay? Was it just, 30 centimeters long, or was it over 2 meters long, okay? You can see where I'm getting at this. And the shape, so all these things are important because if someone wanted to repeat the experiment again, they want to know exactly what equipment or type of equipment they needed to include, okay? So then they compare their results with yours. Another thing that we were looking for, especially in this physics experiment, was the size or shape of the object that was falling. So we decided to use a variety of things. Some of us used little glass cylinders, others used pencil cases, or even little takeaway containers. Now that's fine as long as you kept it all standardized within your treatments. However, so someone could repeat the experiment, we wanted to know the rough size dimensions. So was it a cylinder, was it a square, and what was the maximum mass and things like this, just so we can understand what sort of aerodynamics might have been influencing the results. Hope this makes sense. So so to get full marks for this section, you just needed to not only just list the amount of equipment, but also specify size or dimensions where necessary. All right, now, this is the main section of your methods, really. It's basically going step by step, outlining exactly what you did to achieve your results. Now, in terms of our marking criteria, these were the things we were looking for full marks, okay? So you need to have a feasible method that is, did all the major parts of an experiment, were they included in your methods, or did you omit something really vital? Had to be a fair test, so you had to explain how each of your treatments were a fair test, or a way you can compare them standardized, standardized measure. You also had to have all your control variables listed and things like that, and how they were important and why you chose them in some instances, because sometimes it's not as obvious why you had to undertake that certain step. And a really big one that was really important that a lot of people missed out on was this: specify how variables were measured. Okay, so this is where the most ambiguity was. Okay, some of you might have said measured height, or measured height of what, or you might have just said weighed plant, how many plants, to what sort of decimal place. Okay, just got to be more specific. And finally, an indication that your results were reliable in the fact that you replicated your treatments, okay, through several trials, at least 3 trials. And I think most of us did this, okay? Now, just for some tips for the future, okay? Now, I've alluded to this just now, but sometimes some of our methods need a bit of more explaining or rationale, okay? So, for example, if we use cotton wool instead of soil, we know that's because we didn't want the type of soil or the nutrients in the soil to impact our results, and therefore it was more of a standardized medium for seeds to grow in. But the person who's reading this report might not understand that, and they think, oh, cotton wool, that's a bit of a funny thing to grow seeds in. So you just might want to have a sentence or two saying, well, we use cotton wool to standardize the effect of any potential nutrients found in soils, or something like that. Something short and sweet. Also, a lot of us, we undertook preliminary experiments, which is a really good thing, okay? So you're kind of testing out your experimental design, see if there's any flaws that you might need to fix. Unfortunately, a lot of us, we took that to be our final experiment, and we include the results or the, I guess, the pitfalls in our discussion. Now, it's good that you're noticing how to improve and things, but in the future it might be good to just incorporate these changes earlier on in your poster. That is, talk about in your methods how you might have undertaken a preliminary experiment to increase the accuracy or the precision of your methods, and then moving forward you follow these steps because of that preliminary experiment. Okay, so don't talk about improvements in your discussion. It should, improvements in terms of what you did before you took your final experiment should be mentioned here in the methods. Okay, and finally, I mentioned this at the beginning, it's fine that you use like numbered steps, like a recipe, so to speak. That's fine, we didn't expect anything more, but just remember, as you're moving through into more senior years, it might be good for you to start learning how to change that way of writing your methods into a more of a full paragraph with sentences that flow on from one another. Okay, but we weren't expecting you to do that at this point, okay? And finally, the last section of the methods was the safety analysis. Now, to get full marks for this section, we wanted to have a comprehensive list, so that means at least 3 things, generally, produced in a table format that showed both the risk, potential consequence of that risk, and a precaution that you would suggest taking, or you did take, to make sure that that risk didn't have a severe consequence. Okay, now I've just gone through and taken a good example of one of these safety tables. Okay, you can see here that we have risk on the first column, the consequence of that risk, and the precaution that you would take to make sure that risk didn't cause any undue harm or stress. Okay, and you can see that this person has included 4 different types, okay, which is a good example of a comprehensive list. Now, if you just had 1 or maybe 2, perhaps you didn't score as well. Okay, and we also wanted to see it in this table format, so not everyone included in the table format, so you would have lost points there. Okay, right. That's the methods. Moving on to the results, which is actually the most important part of your poster or report. Okay, it's the most important, but it's also usually the shortest. Okay, and that's because we want to keep things nice and tight, nice and concise, so people don't get distracted and can really just get the main message and let the data speak for themselves, so to speak. Okay, so it's usually at your stage, in your posters, it's usually just a number of graphs or tables, or both sometimes. In this case, we wanted you to do both a table and a graph. But in the future, you might also acknowledge that the results section might be accompanied by a written description of the trends that you found in your experiment or study. But in this case, we just wanted you to include a table and a graph, at least one graph. All right, so we split the results into two different sections. So first we looked at whether or not you included a table and how good that table was and whether it kind of conveyed your results in a simplified manner. Okay, and in terms of what we were specifically looking for in our tables, we were looking for a table that had headings with the appropriate units. Okay, not everyone had the units like centimeters, time, seconds, that sort of thing. And that we had average calculated of the 5 or more data points that you collected. Okay. Now I'm just going to go through and show you one kind of bad example, or perhaps not so good example of a table. It shows the information, but probably not the best way. And then I'll follow that up with what I'll see as a suitable or a well presented table. Okay. So here's the not so good version. You can see that they've included all the information, but there's some things here which could be improved. So this is based on the light-dark experiment that someone might have done with the plants. Okay, putting some in the dark and some plants in the light. Now, they've included all their raw data, which is good. Okay, we wanted you to include that. However, it's quite bunched up. Okay, and it takes up a lot of space, and it includes a lot of empty spaces over here. Okay, because we want to be concise, and that gives you more space on your poster to do other things. Okay, so but other than that, it's pretty good. Also, it repeats the units after each actual raw data point. That's good. It's great that this person included the units, but it would have been more efficient just to have it in the title. So height in brackets centimeters. Okay, and then you wouldn't have to include the centimeters there. And another point is that they haven't included the data points to all the same, well, they haven't rounded them up to the same significant figures. Okay, so it makes it look a bit messy and that sort of thing. So it's good to keep at the same level of significance. Okay, and finally, they've included both the dark and light averages in the same row. Okay. In this case, they should have at least just moved the light down into the right column, because then that gets a bit confusing, and they've omitted the units here anyway, so we don't know what exactly that might mean. Okay, can you see how there's some ambiguity behind that? But overall, still quite clear. They've got the column titles and things, so they wouldn't have got 0 marks if you had something like this. It's just not the most synthesized way of doing something. This is the same data, but presented in a more concise manner. Okay, so instead of having the trials as separate rows, okay, we have them as separate columns. Okay, and instead of having the centimeters after each number, we have them just after the title of the columns, and then we have the average with the units over here. Okay, I just bolded this one because it makes it stand out, because the average is really the interesting data point here. Okay, so this is kind of what would have gotten you full marks. Okay. Another tip for the future, again, this wasn't necessary to get full marks, would have been to include what we call a caption for your table. Okay, now that would have looked something like this. Okay, it's a nice little descriptive sentence or two which describes to the reader, the viewer, what the table is actually all about. So it's not so much a title. Titles are usually shorter, but a caption which goes above a table and below a graph just kind of gives a short little pithy statement about what the results below are. Right, so that's the first part of the results, looking at what it takes to put together a good table. Now we're going to look at the second part of the results section of your poster, which was your graphs. Okay. Now, in terms of our marking criteria, these were what we were looking for. We needed to see that we had the labels, it chose the correct type of graph, they had the units on both the axes. Okay, so these centimeters if it was growth, or say grams if it was the weight on the x-axis. And overall, we wanted to see that the graph presented your data in a clear and concise manner. That is, we didn't have to look too hard to see what your results were trying to say. Now, just like I did with the table, I'm just going to go through and give some examples of what some good graphs would have looked like and some not so good graphs. And just so you can kind of see what we were expecting and what all these features look like when they're featured on a graph. Okay? So, if you were to do the physics experiment, that is looking at how fast objects move down a ramp of varying gradients, or in this case both weight of an object as well as the different gradients, we'd expect you to produce a graph similar to this. Okay, so in this case I've chosen to use dots instead of columns. In this case either one's fine, but because we have what's called a continuous variable on the x-axis as well as a continuous variable on the y-axis, I prefer to use dots in this case. Okay. Now you'll see here we have two independent variables. Okay, the first one, which is the weight of the object, that's plotted on the x-axis. Okay, most of you probably would have only had one independent variable. Okay, and that would have had to go on the x-axis here. Okay, the second independent variable is this slope of the ramp up here in terms of degrees. Now, because we're putting the dependent variable here on the x-axis, that means that the dependent variable goes on the y-axis. Okay. In this case, the time it takes for the object to slide down the ramp, and you can see here that we've put the units seconds after each of those, and over here we have grams to indicate what sort of units we're talking about here. Okay. Another thing in terms of aesthetics, you'll notice that the writing isn't too small. A lot of us tended not to increase the font size, and it was really hard to see what the numbers were, as well as if you did include axis titles, sometimes the font was too small for us to read. Again, you just make sure that it's aesthetically pleasing, that is, that we can easily see things without having to kind of get right up close and squinting to look at it. Another thing that some of us forgot to do was use a legend to indicate like what the different colors or shading might have meant on our graph. So this would have been our second independent variable in this case. Now, having said all that, we can now easily see the trends or the patterns in the results, where we can see that as the weight of an object increased, regardless of the slope, they all seem to decline in the time it takes for them to reach the bottom, which makes sense. Likewise, if we just kind of looked at the different slopes, we can see that as slope increases, okay, the time it takes for that object to move down the bottom also decreases. So if we combine both these factors, we could say, looking at this graph quite easily, that the overall trend is that as the weight of an object as well as the slope of the gradient increases, so too does the speed of that object. Or in reverse, you could say, so too does the time it takes for it to travel from point A to point B is reduced. Okay, so this is what I'd say is a good graph. This would have got you full marks. Okay, so it has all the appropriate elements. Notice there's no title, so to speak. That would come later in a caption underneath if you really wanted to, but in this case we weren't looking for a title. If you really want to go above and beyond and really show your graphing skills, you could include what's called trend lines. Okay, these are not the same as connecting the points. You'll see that these trend lines don't connect the dots. That sort of graph is reserved for something different. Usually when you have time on the x-axis, that's generally the only time we connect dots. But rather, these trend lines show your overall pattern or trend. That's why they're called trend lines of that data point. Okay. Again, this is kind of like a higher order sort of level thing. Sometimes it's hard to do if you're not very good at using Excel and other data plotting techniques. But that's okay if you didn't include trend lines. Sometimes it just makes it helpful for the reader to see the overall patterns. Okay. Here's an example, a good example of results from say the plant experiment, that is looking at how different factors like light or darkness or amount of water, in this case both of those, amount of water and light and darkness. So again, we've got two independent factors. Again, not everyone would have done an experiment that's that tricky, but I thought I'd just show you what some of us in Year 8 are capable of doing. So again, we have both the X and Y axis labeled with the correct units, in this case percentage, and millimeters here on the X axis. Now, the reason I've chosen the column graph as opposed to the dot or scatter plot is because this independent variable is what we call categorical. It's not continuous, okay? We've chosen discrete units, okay? So from 5, 0, 5, and 10. It could also been described as low, medium, and high. That might have been easier to see that how it's categorical, okay? Whereas the other one, it was continuous. That is a number going from 0 anywhere to infinity, really, but we chose to stop at a certain point, of course, because we can't keep going up to infinity. In this case, again, we have the two different independent variables labeled here. One is a legend, and we have the dependent variable on the y-axis, okay? In all cases, this is what we do. We want to have the first or only independent variable on the x-axis and the dependent variable on the y, okay? Again, and this is demonstrating the averages or the means, not the raw data, which is one of the pitfalls that some of us fell into. So again, this is an example of a good graph. We have nice size fonts, it's easy to read, and nice and colourful. Now here are some common things I was saying that some of us kind of fell into. So the first one here I'm trying to demonstrate is that, well, if we're looking at percentage germination over here, okay, I haven't labelled the graph in this case, of the axis, sorry. We can't see much difference between our treatments, and that's largely because our scale could have been adjusted, okay? So most of the data points exist above 80%, so we could have started our y-axis at 80%, and that would have drawn out these differences or made it much more easier for us to see the differences. So if you are working with percentages normally, you find that most of them have a high percentage. You don't always have to start at 0 here. You can always start at a higher number just so you can draw out the differences at the top. Another pitfall, like I mentioned to before, is that we included our raw data or our trial data. Now, generally speaking, in scientific reports, we don't present our raw data, we present our averages. That's why averages are more important, because they show the overall trends. Sometimes, if we have important points to make by including raw data, we use that, we put that into an appendix at the end of our report, or on the opposite side of our poster. So it wouldn't have been appropriate here in your poster to include the results of trial 1, trial 2, trial 3. We would have just wanted you to see the average, the differences in the averages, okay? And finally, this is an example of an incorrect type of graph. So I mentioned before, because this is categorical, that is the discrete categories, okay? So there's low, medium, high. We would have preferred to use a column graph, not a line graph that connects the points, because again, we only use this type of graph, generally speaking, when we're looking at time on the x-axis. So how one particular thing changes through time, okay? So these are just some of the pitfalls that you should be looking out for in the future.